Hello, I'm Marc Juarez, and I'm presenting our work titled A Crack in the Bark, Leveraging Public Knowledge to Remove Tree-Ring Watermarks. This is joint work between Junhua and myself at the University of Edinburgh. In this paper, we evaluated the security of Tree-Ring, a popular watermarking scheme for image generation, and showed that we are able to remove Tree-Ring watermarks without a significant impact on image quality. In this presentation, I will explain our attack and the broader implications it has for AI safety. Let's start with some context. As you probably know, the quality of generative AI has improved dramatically over the past few years. In less than a decade, AI face generation has gone from blurry, pixelated faces to realistic images that are nearly indistinguishable from real photographs. This rapid improvement has outpaced regulations and technical means to distinguish real from AI-generated images, raising serious concerns about the risks of misusing these technologies. Here are some examples of how these risks can have real-world consequences. In the first example, on the left, we see a deepfake of smoke rising from the Pentagon. This went viral in 2022 and even caused a dip in the S&P 500. In the center, there's an example of personal harm. AI has been used to generate explicit content to blackmail and harass individuals. And finally, deepfakes have also been used to manipulate specific voter demographics in elections. So this shows that deepfakes can be weaponized to cause various types of harms. This is why we need tools that help us tell apart deepfakes from real images. Various techniques have been proposed for this purpose. A popular approach is post-hoc detection based on features that distinguish deepfake from real. However, this leads to an arms race between generators and detectors. When detectors find a distinguishing feature, then generators improve their models to refine them so that they no longer exhibit this feature. Watermarking breaks from this arms race by embedding an additional signal that can be reliably detected. If the watermarks are robust enough that they cannot be removed, then they have the potential to mitigate some of the risks. In particular, we are interested in in-processing watermarking, where the watermark is embedded as part of the generation process itself, as opposed to post-processing, where the watermark is embedded in the image. This approach has received increasing attention because it has been shown to be more robust to removal. Okay, so to understand how in-processing watermarking works, let's briefly review how to train an image generation model. We will focus on diffusion models as they are the most popular models for image generation. These models are based on a stochastic process called the forward diffusion process. In this forward diffusion process, we start with a clean image and gradually add noise in a series of small steps until we are left with only noise. Then we train a machine learning model that learns how to reverse this process. Given the noise and the original image, it learns how to remove the noise to recover the original clean image. More specifically, we typically use a U-Net architecture for the model, as it's very good at denoising tasks. If we do this process many times across many images and noise levels, the U-Net learns how to model the underlying data distribution, and in addition, it also provides a method to sample new images from that distribution. Okay, so to generate a new image, we simply start from a noise sample, and we use the trained U-Net to iteratively remove the noise, eventually producing an image. All right, so now that we know how to train a diffusion model, how can we watermark it? We'll see this for Tree-Ring, which is a very popular watermarking scheme. Tree-Ring works as follows. First, it takes the initial noise. This we usually call the initial latent, okay? And it transforms it into the frequency domain using the fast Fourier transform. And then it embeds the watermark key in the center of the frequency domain. This corresponds to the low frequency region. And this key is formed by a sequence of concentric rings, each ring with a different value. And once we do that, we transform it back into latent space and feed it to our diffusion model to generate an image as usual. Optionally, we might also provide a prompt to guide this diffusion model. It's important to note that the diffusion model is not known to the attacker. Okay, if the attacker knows the model, then they can trivially invert the process and recover the initial latent where the watermark is. This assumption is realistic because most advanced diffusion models are proprietary and the model details are kept confidential. Okay, so now if we're given an image, how can we verify that whether that image has been watermarked or not? So what we do is we invert this process. So we go from an image to the latent that was used to produce that image. For some diffusion models like DDIM, we can do this with sufficient level of accuracy. Then we convert that into the frequency domain and check the center region and compare it with our watermark key. And if they're similarly enough up to a threshold, then we conclude that this image contains a watermark. And this is very clever. However, under certain assumptions, as we will see now, these watermarks can be removed. Okay, and the vulnerability stems from how modern diffusion models actually work in practice. Most state-of-the-art diffusion models are trained via latent diffusion. This means they don't work directly on the pixel images, but on a compressed representation of the images obtained using an autoencoder, typically a VAE. Okay, we call this the intermediate latent. This process, latent diffusion, significantly speeds up training and fine-tuning diffusion models. And actually, for this reason, VAEs are often published and reused so that people can develop diffusion models much faster. For example, OpenAI's DALI VAE is public, okay, and has been used for training and fine-tuning other diffusion models. This, however, and this is one of the key points of our paper, can be an issue because if the attacker has access to the same VAE of the diffusion model, then they can perform attacks in the intermediate latent space. But why having access to this intermediate latent space is a problem? What we found is that the watermarks are still distinguishable there in the intermediate latent space. In here in the top row, we see the latents of watermarked of steps of the diffusion process for latents that have been watermarked. And as you can see in these orange boxes, we can still observe this circular, these rings like pattern, even in this last step, which corresponds to the intermediate latent representation. And if you're not convinced by this image, we also trained the classifier to distinguish between watermark and non-watermarked latents. And what we see is that we can perfectly separate the two classes. Most importantly, this classifier can act as a surrogate of the watermark detector, which enables gradient-based attacks. So since we know the parameters of this detector, we can mount a gradient-based evasion attack that evades the surrogate detector and that may actually transfer to the actual detector, meaning that if we can do that, then we are able to remove the watermarks. That's basically how our attack works. Okay, so in more detail, the attack has two stages. In the first stage, we train the surrogate detector. And to do that, we generate a data set of both watermarked and non-watermarked images. We then encode these images into the latent space using the public autoencoder. And then we train a simple neural network to act as our surrogate detector. Recall that we don't need access to the target model weights. We only need the surrogate and the detector of the detector and the public autoencoder. And we evaluated the case where the attacker's autoencoder matches exactly the one of the targeted model, as well as settings where the attacker may not know the autoencoder, but they may have access to other public autoencoders that are similar and that can be used for the attack. Okay, so now the question is, how does this attack transfer to the actual detector? So do the instances where we can remove the attack for the surrogate, do they also bypass and fool the actual detector? So to answer this question, we evaluated the attack and compared it with various baselines and state-of-the-art removal attacks. The results are shown in this table. We evaluate various performance metrics to measure the predictive performance of the detector, as well as the impact on image quality. In the first row, we have the no-attack baseline, and we see that the detector in this case achieves above 95% accuracy. And in the bottom row, highlighted in yellow, we have our attack. And we see that the attack is able to reduce the accuracy of the detector to basically random guessing, while the impact on image quality is very low. And we actually have verified this manually and by checking the images after removal, and the removal of the watermark is imperceptible. These rows here correspond to the setting where there's a mismatch in the autoencoders, and what we see is that while the attack still decreases the detector's performance, the decrease is much smaller. So this means that the attack can remove the watermarks while preserving image quality overall, but it's particularly effective when the autoencoder matches the one of the targeted model. Basically, when that autoencoder has been made public. So we also perform various ablation studies, and we highlight this one, where we vary the intensity in terms of the magnitude of the perturbations of the attack in the x-axis. And here on the right, we have the results for our attack as I explained it. And this is following the same strategy, but instead of applying the attack on the intermediate latents, we applied it on the raw pixels. And what we see is that at the same attack intensity, our attack achieves a higher drop in performance with a limited impact on image quality. So this means that operating in the latent space is much more effective at removing the watermarks with actually having much of an impact on image quality. In our evaluation, we also measure the precision of the detector. We found that this metric is often overlooked in watermarking research. Previous works mostly evaluate schemes using balanced datasets. However, this can lead to the base rate fallacy, as in deployment settings, the base rate might actually be much, much lower, okay? Especially in early stages of the deployment where most of the images will be non-watermarked. In those cases, even if accuracy is very high, precision can be very low. This graph on the right shows precision in the no-attack setting for various true positive rates. So here we chose a specific operating point for a given true positive rate. And in the x-axis, we have the base rate, hypothetical base rate. We see that precision is low even for quite high true positive rates for base rates that might hold in realistic deployments. So we also evaluated this with when the detector is being attacked, and what we see is that the attacks make this problem much worse. They lower precision even further at the same base rate. So we encourage you to check the paper for more details. Okay, so let me summarize our key findings and their implications. First, our attack consistently evades tree-ring watermark detection with minimal impact on image quality. This highlights the risk of reusing the autoencoders, which is a threat that is overlooked by current practices. When the autoencoder is publicly available, what we see is that this gives an advantage to the attacker, and our attacks basically defeat the detector in that setting. Second, as a countermeasure, obviously a straightforward countermeasure would be to design watermarking schemes that are indistinguishable in the latent space. Okay, and even better would be to design watermarking schemes with formal security guarantees. And we already see new watermarking schemes being proposed that are making progress in these directions. And finally, our analysis reveals that tree-rings precision may be insufficient for real-world deployment when the base rate of watermarked images is low, especially in the light of our attacks. So we urge researchers in this field to include precision in their evaluations, following the methodology of other security domains where the base rate and the base rate fallacy are a very well known issue. So this concludes my talk, and I encourage you to read the paper, and please reach out to us if you have any questions or you want to discuss anything. Thank you very much.